Hello everyone, it's September the 1st. Alright, so today we have an easy one. Let's just get that one done, and we have to get back to the minimum jumps. Oh my god, minimum jumps. What a mess with minimum jumps. Alright, given the root, return the average value of the nodes on each level in the format of an array. Average value of each node, of all the nodes on the level. So BFS, right? Okay, so we got lucky. Today is easy, so let's just get it done and go for the kill with 1654. I think what's gonna happen with 1654 is I'm gonna read the hint, and when I read a hint, after we read the hint, we will try to see if we can get it done. Right, that's that. And then we say, oof, I have called node, it's not value. Ah. Like this. This one. Right. Once we're done, let's see. This one shall be right. Okay. Oh, there's so many different methods, huh? I don't know. I don't want to do all these methods today. The main goal is the jump. Alright, so none of these methods work. So we have to go back to the hint. So what's the hint? Topic, DP, BFS. DP and BFS, that's interesting. Well, it just means I was completely in the wrong. Okay, BFS. We want a minimum number of steps to reach. I think I tried BFS, but it didn't work. It's like, how do I know? I mean, I can see how BFS work, but we tried that, and that also didn't work. Because we were starting from the end, right? And I mean, we can start from the front. It's also okay. Yeah, but the problem is, how do you know you cannot reach? Let's see the hint. Think of the line as a graph. What line? That line, okay. To handle the no double back jumps condition, you can handle it by holding the state of your previous jump. Think of it as a line, as a graph. What do you mean? So the line is just 0, 1, 2, 3, 4, right? And we think of them as a graph. Okay. Holding the state of your previous jump. The hint didn't help me at all. Okay, we try to see if we can reach a certain node. So and we can always find it, right? Oh, this hint didn't work for me at all. By holding the state of your previous jump, what does that even mean? Like if we do a back jump, so we can only go forward, right? I mean, we can configure how many back jumps we need. Well, we can, like, from here we go front, right? Then when we go front, then we can go back, or we can go front again. So now we branch out. And if we go to the original state, then we don't do it, right? Hold on. What he's saying is if we go, so we have to go right first, right? That's the first one. And from this, we can say, okay, I can go from each node, I can either go back or I go forward. But if the previous one's going back, so I can only go forward. So now we see if the node has been visited before. If it has been visited before, we just don't keep going. If it has not, then we just keep going, and then we try to see if we can reach the target. But how do we know if we can reach the target? So we just keep this game going, right? Going forward, going back, going forward, going back, and we can now go back 2 times in a row. So kind of limiting how many new states will be created. And eventually, after a while, we'll end up with a situation, because if, think about this, if we move to the right more than we move to the left, okay, then eventually if we end up at a value larger than x, then we can never go back, right? That's one observation. So if a is larger than b, if a is larger than b, like this situation, and then if we just traverse, and then if at a certain point all of the value is larger than x, then that's impossible. If a is smaller than b, if a is smaller than b, then it is possible, because we can do multiple a's and then do a b, so we can create a lot of scenarios, right? We can create a lot of scenarios. So, but how do we consider if something is not possible? Well, because each time we can only go back once, and we can go forward any number of times we want, right? Which means, like in the first case, we can go back 12, 9, right? 6, 3, 0. We can stay in the same position, and we can go forward 3, 6, 9. So that's like each time, if we consider the backwards as the differentiation point, right? So this is all the positions that we can reach in the first case. And from each position, we can go back to these. In the second one, it's always positive. So we only go right. Right? We go one time right, one time back. That's 2. We go 2 times right, one time back. That's 17. Right? And then 32. And then 47. So it's always plus. Right? It's always plus. So we want to see if we can reach 11. So any combination of these can reach 11. Well, because we can never go backwards. So any plus is more than this is not going to do. So we can only consider plus 2, right? We can only consider plus 2. And for plus 2, it's not going to work because 11 is an even number. We cannot do plus 2 to reach 11. Okay. How about this one? 16 and 9. So we'll have plus 9, 16 as well, so plus 7, right? And then 7 plus 16. Yeah, so basically it's 7, and it's 7 plus 16 times 1, 7 plus 16 times 2. These are the moves we can get. And actually, these are easy to reason with. Right, no matter how you do, it's always going to be 7 plus 16 times something, right? For this case. Because we consider going a certain way right and then going back, going a certain way right, going back, right? So all of these can be just little chunks. And every time we're going right and going back, that's plus 7. And the rest has to be multiple of 16. Then the question is, 7 plus 16k equals 7. Is that possible? We say, okay, how about k equals 0? Now if k equals 0, that means we do, the k is the additional, right? It's like the additional, yeah, so we don't do additional, we just do 1. Well, we can only do 1 because we're going right? We can only do 1. So we say, okay, can 7, yeah, can it work? Wait, hold on. No, that's not right. It's we can plus 2 plus 2 plus 2. So we can plus 7 plus 7 plus 7. We can do any combination of them. But again, if we're going right and it's larger than this, then we don't consider them. then we consider if that's possible. And then this one is say, okay, 7 is equal to 7. That's the only thing, which means we do a right and do it back. So we have hit 9, 16 and have hit 9 and see if they're in it. Okay, they're not in it. So what if you hit something more complicated? Like in this case, okay, we say go right. Go right is 61. Go left is 170, right? So we have this 170 minus 61. That's minus 109, right? So our delta is going to be minus 109 plus 61 minus 109 times plus 61 times 2 and all that. So now the question is, any combination of this can reach 135. Yeah, that's the thing. Like you're analyzing it, right? Doesn't seem to be working. What if we just traverse it? We just go. Why don't we just go right, and then we can decide go back, or we can decide not to go back. We go right twice, decide go back, or not go back. Right? If we go back already, we just keep doing this, and if we hit forbidden, we just don't go. And for the impossible, for the ones that eventually give us -1, those are the difficult ones to deal with. Yeah, I think the -1 is the only thing I'm worried about, because I don't know if this sequence can keep going. And eventually, we'll reach a state where we only go back. If we cannot go back, definitely, that's an easier problem to solve. Yeah, what would this one look like? Well, we'll hit a lot of values, right? And they will miss 11, right? Because we can hit all the even numbers, but we can hit none of the odd numbers. How do we know? Like, I won't know the current state, right? And if I go, yeah, like if I know the current state, and if I make the next move, then that one will be, yeah, that one just don't go. But we can always go right. We'll always have something go right. So there will always be something that's getting bigger and bigger and bigger. What will it eventually be? We just have big values because we keep moving to the right, keep moving to the right. Right, we keep moving to the right, keep moving to the right. Yeah, if we move left, it can be more. Then we always have a chance to reduce, right? We always have a chance to reduce, and then we'll know how much reduction I can do. Okay. Okay, so I know how much reduction I can do. So I can do 2, and then we go back. Right? We always know. Or are you saying, as long as we can go back, we should always keep trying? Man, I'm pretty sure that's not true. Or maybe like if we run out of everything to go, and all we can do is just keep going right. Yeah, if we go right and then go back will be larger, we will hit a situation, right? I mean, we might be able to get the occurrence. I have a new idea. We can get the occurrence. We can know how many steps it's going to take to reach all these values. And they're always going to be from a certain value going back, right? Going back. Then we can calculate, okay, how many we can reach here. Right? And then, can we always get back? Is it cyclical? Yeah, always something. It could be cyclical. So x, a minus x divided by b. It has to be, because I'm going to go 1, 2, 3. So in that case, 15 times 13, right, minus 11 divided by 13. Wait, okay, that's not wrong. That's not right. Is that 12? Minus 11 divided by 13. Yes. Can we keep going on? So like we have 25, 0 first. If we miss it, what's our second? Still no clue. Find the next target. Just keep going, right? Keep going. 13, 14, 15. Eventually we'll find it. And then we keep going one step at a time. And when we reach it and it's no good, try the next one. And when do we stop? Like seriously, this is a question. When do we stop? Yeah. I don't know. I'm gonna give up. Bidirectional BFS. Yes. Yes. Bezout's identity. What's Bezout's identity? Yes, that's basically my point, right? We don't know when to stop. Because if we know that it can reach an end, we just BFS it. It's very simple. But what if we can't? Proof that maximum search is capped at a plus b plus maximum x. Ooh. All reachable position must be a factor of GCD. For some integers x, y, z, and ab, x times a plus y times b equals z times Yes, we realized that too. We realized this. Yeah. If A is smaller than B. Yes. Must search at least past. Yeah, because we can go past X. And then we can always go back unless it's been blocked, so it has to go past forbidden. What we need to find a starting point. The first reachable position is the first position such that P is larger than max. All positions P0 plus M are reachable. That is true. That is true because you're beyond forbidden. If you're beyond forbidden, all of them are reachable. Okay, so the argument is we want to go, like we can go beyond, right? But we just don't know how much beyond we need to go. So we say we have to reach at least beyond the maximum forbidden, right? Because you can always go back, okay? So we start from max underscore, and you can only go forward. You will end up at position. What is this position? Oh, it's supposed to be, oh, you cannot reach this. Okay, I see. We can first reach our for these positions, we can reach them from beyond by going back. Okay, hold on. Let me read this again. At some position. Wait, what's P0? P0 is beyond this max. MP0 plus A. Because we move from this, we have to go A. And then minus will go back. Sorry, this I don't understand. go through this one more time. Yes, I'm end up at some position, which is P. It's P0 plus, what's P0? So P0 is the first one is larger than the max, right? Now we know that beyond the forbidden, we can always come back. The problem is if we can reach certain position the first time, we might be able to, no, not we might be, we will be able to reach it again from coming back, because all that is to it is a multiple of GCD, right? It's just a multiple of GCD. We add some and then we minus some, right? So I'd say this is the impossible, this is the forbidden, and this is the first one that we can reach beyond forbidden. So from this point, what do we do? So we're here, right? Anything to my right might be retraceable, right? So we want to know beyond a certain point, all of these can be retraceable. Which means that should be the first one. If I hit here, if I go beyond, wait, hold on. If I go beyond, then what? If I go beyond the boundary, I still don't understand. So when we go beyond, because we have to go back, but you already go beyond, so it's always shorter to reach that instead of going back. Okay, that makes sense. Which means if you want to reach, if you go beyond a certain point, then when you come back, then those points must have been visited already. All right, so we just need to find something. So when we reach beyond that point, then going back is gonna be more steps. Right, so we want to find a point, right, find a boundary where if we go beyond, then it will always be more costly to going back. So we don't go beyond, we go to this point. This is the boundary, right? This is the boundary, so we cannot go beyond. Which means if we go beyond, you have to come back. and then those points that we already hit, right? If we go beyond, we go back, we hit those points we already hit. So where is the boundary? And then for one thing, we have to check beyond the forbidden. So we go beyond the forbidden, and then we can just freely move, right? Then we want to find the first point, right? The first point that is beyond the forbidden, that we can find. The first point that's beyond the maximum, actually, or beyond the maximum. So that point will be reached, right? Then what? Then we can go, yeah, so like it's within this point, then we need to go back, then we'll hit those also for the first time. It is a point where if we go beyond, then all the points before has already been visited. That's the point. That's the point we want to find, where if we go beyond this point, then there's no point of going, because all the point that those beyond want to go back to, they have already been visited, right? Okay. And the thing is, when we reach a point, GCDAB is not a multiple of A. I still don't understand this explanation. plus A minus GCD. Now, A is a multiple of GCD. I think that's what it means, not the other way around. A is a multiple of GCD AB. That is true. So we can go this, or A minus. That is perfectly fine because A is a multiple of GCD AB. So this one is also a multiple of GCD AB. But isn't that one of these things, right? Isn't that one of these guys? Yeah. That's the first one we can reach, is we go A. This is the maximum we can go, is we go A, right? And then we go back. So GCD AB is the smallest value we can go back on. So the maximum we can reach is this for the first time. Because let's just go A, right? I mean, but go A is the maximum, actually. And then minus GCD. Well, A equals something times GCD. think I got it. A minus GCD AB plus B is the furthest we can go. No, that's actually no. It's maximum. It's GCD. It's n times GCD AB plus A minus GCD AB plus B. This is the largest we can go. And we know n times GCD AB must be larger or equal to the maximum of x and forbidden. Right, this must be larger than this. Which means this one minus GCD AB is smaller than maximum x and forbidden. So we have this minus this is something smaller than max plus A plus B. And the boundary shall be this max of this plus A plus B. Yes. Okay. I think I understood. You know what? I'm gonna code it tomorrow. But what's this bidirectional? I think we just start at both ends, right? And then once we go beyond this boundary, we just cut it off. And then we just always go left. And of course, it's going to be BFS, and we have to record the state. It cannot be going more than what we need. And then we can go bidirection. I mean, why would we go bidirection? It's the same thing. I would go single direction, bidirection. And what's the benefit of bidirection? Are we going fewer number of times? We are going fewer number of times because each step is, so we're going the same time, right? We're going the same time, one step here and then one step here, all right? And then next step. So we go one step first, and then we check. No good, we'll go one step here. All right, and then we go one step here. So that we check first. Okay, we check first. All right, we check. How do we check? So for each one coming out, we see if it's in one of these. If it's in, then we're done. We already reached. If it's not in, then we move a step. And then going to them, they will check as well. So we check on both sides. Okay, I will stop here. Tomorrow we're going to write a solution, and I will write my explanation for this thing. All right, I'll see you guys tomorrow.